Okay, some more advice if I could give some. I always give kids my notes in advance. And the reason why is I don't want you guys spending your time, pardon me, I don't want you spending all your time in class frantically scribbling down stuff. You probably had a teacher before where there's notes on the board and you're really not listening, not because it's not your fault, but because you're so busy trying to write all this stuff down like this. And then all of a sudden you look up and it's changed to the next slide. And you're like, oh, okay, can you go back? And then after a while you're like, I'm just not going to ask. And you whisper to the person next to you, hey, what was that? And you get in trouble. Been there? Okay, fair enough. So, as a way for me to try to fix this, I'm going to give you the notes in advance. Now, this isn't meant to be like a cop-out where, well, oh, I've got them now. Like, what I want you guys to work on now is rather than writing stuff down, focus on what I'm saying, highlight, and write down what like we talk about in the margins. Does that make sense? So whenever I make like little notes on here, write those ones down. But like the bulk of what we need is already waiting for us. Does that make sense? Okay, let's get started. We're going to do physics. Okay. I've been looking at how we're going to do this whole grade 10 to grade 11 thing for those of you who need to do like the recapture of Science 10. And one of the good things is that this lesson right here I'm about to give is actually exactly what I would give to a grade 10 kid. So this is it's actually going to work really, really well. We're going to talk today about speed and velocity, which yesterday when I was just kind of making stuff up was actually what I talked about then too. So the goal of this unit, by the way, the overarching picture, we're talking about collisions. Okay, if I didn't make that clear yesterday, they want in this curriculum for you guys to be able to know a little bit of the math behind how mostly cars crash, I think is kind of like the big picture, but like we can move this into other areas. Okay, what do I start reading here? Big picture wise, physics, just so you guys know, is the study of natural things, like how things move. You know, like for example, if I take the stapler and I let go, what's going to happen? Okay, you guys have experience in life such that you know that things fall, right? That would be a natural thing. What natural phenomenon am I describing, though? Yeah, gravity. You guys know that word, right? Gravity? Right? And so that would be a good example of a natural phenomenon. How, like, energy and matter move. You guys know what matter is? Ever heard that word before? What's matter? Like put matter into like people words. If I said, hey, what is matter? Not what's the matter, but like if I say what is matter, what would you say back to me? Matter is, what'd you say? Sure, that's way too technical still. Dumb it down a little bit even. Make it even simpler. Matter is not necessarily space. Matter is like stuff. That makes sense. Like matter is like the stuff we have. Right? Like this is matter. This is matter. The air around us is matter. Is fire matter? Why not? What is matter? What is fire instead? Yeah, there's really two things here. There's matter, which is our stuff. This would be something you could write down, by the way. So like matter is like our stuff. You know, Jaden, your definition was fine, by the way. Just so you know. But like, you know, like it's the things that things are made of. It's the stuff we have. Right? Energy, though, is like, how do you describe energy? Energy is like what you do with it. Like how you move stuff. Yeah, that's a good way of putting it. Like I'm giving you like the basic definition. Obviously, there's more technical definitions here. But does that make sense what I'm saying here? So here's a stapler. Does this stapler have energy? Well, what if I let go? Is it going to move? Then it has energy because it has the ability to eventually move. Does that make sense? Light is a form of energy. It's going to do something for us. It's going to let us see. Heat is kind of a form of energy. So fire is energy. Does that make sense? But like the stapler itself, we call that matter. So long story short, physics is like the interplay between like the stuff we have and what makes the stuff do stuff. Wow, I'm really technical. I'm a good science teacher today. That makes sense, though? Say people words. Okay. The rest of this here, you guys can read. It's not really something I would assess you on. But like, if you take enough physics, the whole point of physics is to try to figure out how our universe behaves. Why do planets go around in circles? Why does my stapler fall? Why does, you know what I mean? Like, whatever the question happens to be, we're trying to figure out how our world works, basically. And there's kind of two types of physics. There's classical physics, and there's modern physics. You guys don't need to know this, by the way. That's not really the point. I'm just giving you an overview. Anybody watch Big Bang Theory, the TV show? Okay. The guys who are in Big Bang Theory on the TV show, they work in modern physics, where they're talking about really weird, strange, new age stuff. Classical physics is really basic, where it's like, if I throw something, can I predict where it's going to land? You know? And so if you were like a NASA physicist and you're trying to figure out like where exactly is the space shuttle going to land on the moon, that'd be like classical physics. You know? Modern physics, they're working on things like black holes, dark matter, string theory. You ever heard of any of those sort of things before? I know nothing about them because if I did, I'd literally be a physicist. So, anyways, that's what physics is. So on this slide here, I talk about, again, the idea that physics is about energy and matter, the interplay between the stuff and what makes our stuff move. Okay. What we have to do, though, is know the word qualitative. And for some reason, I don't have the other word written down here. Can you write down the other word? It's called quantitative. There are two words you guys need to know. Qualitative and quantitative. Anybody ever heard those words before in their lives? Okay, I'm going to give you some examples then, and I'll see if you guys can figure it out. I am cold. That is a qualitative result. It is minus 23 outside. That was a quantitative result. What's the difference? What does a quantitative result have that a qualitative didn't? Let me just say them again. A qualitative result was it's cold outside. A quantitative result was it's minus 23 outside. Try it, Jackson. Yeah, one has a number. That's really the only difference. So if you want to write this down here, I actually wrote it here, although this is the wrong word here. This is not qualitative. Can you guys change this? This should be quantitative. If we ever have a quantity has a number associated with it. And that's what we're going to focus on a lot in physics, is anything that you can measure with a number, that's a quantity. If I give you a quality, not that qualities don't count, but I might say that, like, I don't know, this stapler looks really nice. That's a quality. This is a nice stapler. A quantity would be this stapler can staple 75 staples a minute. As soon as I said the 75 staples a minute, now I've actually given like a numerical weighting to it. Does that make sense? So that's my goal, is we need to focus on these measurements. So that is a quantity. Quantity. Okay. And here in this little slide right here are some of the quantities that you may learn at some point. Okay. You know most of these. Like, say, length. Like, how far is it from here to the door? If I asked you how far it was from here to the door, you'd say it's 5 meters. Right? So a meter is a unit of measurement. Or like we weigh things in kilograms. I'm not going to ask you how heavy you are. Obviously, that's rude. But like, you know how heavy you are in mass. Right? Temperature is measured actually scientifically in something called kelvins. Anyone ever heard of those before? Doesn't overly matter. We also measure in degrees Celsius or Fahrenheit, by the way. Those are other measures we have. We measure time in seconds. We measure amounts of stuff in moles. Current is in amps. Light intensity is in candelas. I don't need you guys to know that, but like, does my point of like the fact that we measure things, does that make sense what I'm saying here? We need to measure things in physics. No one is going to be a good physicist by saying, from a physics point of view, the stapler looks really nice. That's not physics. You know what I'm saying here? But if I were to like quantify it for you and say that like the rate of speed of the train is 9.5 kilometers per second, okay, now we're starting to get into the physics realm. Sure, yeah, that is really fast, isn't it? I was just making that up. Okay, so the first things, this is probably the first thing we actually need to know something, because this is something I will assess you on, okay? Scalar and vector are the two words you need to know. Scalar refers to just literally, how much is it? Vector, you guys can even read here, it says how much, but it also tells you which way you're going. So, like, here's the example I've got in my notes. I traveled 100 kilometers. Well, which way did I go? Left, down, up, right, north, south, right? So scalar measurements are kind of half useful because you don't actually know which way you're traveling. Whereas a vector measurement, not only do you get to have an amount, a quantitative amount, but you also get to know like which way. So let me give you another example. I drive from here to Lethbridge. Right? So if I drive 60 kilometers, that's a scalar. But if I told you that I drove 60 kilometers east, By just me telling you the direction, now we call it a vector. Does that make sense? Okay, let's try a quick little game here. I'm going to give you an amount. You tell me whether it's vector or scalar. Handle it? Okay. I weigh 200 pounds. Vector or scalar? What direction was it? I didn't give you a direction. Does that make sense? So because there was no direction, it's scalar. Did you get them backwards? Is that okay? That makes sense then? Okay. I'm going to walk 5 meters east. It's 24 degrees outside. There's 100 milliliters in a water bottle. Good. I'm running out of ideas. The magnetic field of the Earth is 5 Teslas towards the North Pole. Okay, yeah, I'm kind of giving it away now. Okay, you guys have the idea then, right? So, vector and scalar is pretty easy. You just need to know which one has a direction or not. So, in terms of more vocabulary then, we're going to start really basic. We're going to talk about how far something is. If I ever give you a distance or a displacement, they both kind of mean the same thing. Both of them mean how far you go. But one of them is how far, and then one of them is how far plus which way. Okay. So to make sure you have them right, distance is the scalar one. Oh, is my board working? Yeah, it is. Distance is a scalar line. So like, as a good example of a distance, I walked 50 kilometers. That's a distance. And the way that we represent that usually is with like a letter. Usually it's D. D is distance. Easy enough? Okay. Now, if you ever care about the direction, what you do is you put the D still, but you put this little like arrowy thing on top of it. And that little arrow, you guys see this little thing I got right here? We call that like a vector symbol. It means if you ever see one of those, you have to have the raw number, but you also got to give me a direction as well. Sure, can you grab that door? Thanks. So like in this case here, I'd go 50 kilometers up. Yes, we're going up. You see how that's the only difference between the two? Is that this one is just a raw value, and this one right here is a value plus a direction. The only difference then is sometimes we put this little hat thing on top. Easy enough? Okay. Let me show you something else here. This little thing I've drawn right here is another bit of notation, and I think this is what usually makes kids start to get freaked out about physics, is they see this sort of thing written on the board, and they go, whoa, what does this mean? So let me try to break this down for you. Now that we've talked about what the little arrow hat here means, what does the arrow hat mean? Yeah, you need to have a direction. And what does the D mean, though? Yeah, we actually use the word displacement, though, by the way. If we ever talk about a direction being included, we call it a displacement. Now, you see how there's a little 2 afterwards here? Well, this means this was your second displacement. This was your first displacement. Okay. So let me give you an example here. Let's say that you were on the track, and you just so happen to start running at the 10-meter mark. I don't know why, but for some reason you're at the 10-meter mark. That would be like your first amount. And let's say that that was 10 meters east. I'll put like a bracket E around it. And let's say that you ran the rest of the track. So let's say it was a 100-meter track. You ran from the 10-meter mark, and eventually you finished. Let me erase this here because it's a little full. Let's say that you finished at the 100-meter mark. Sorry, I'm running out of room here. Let's go east. I'm asking you to subtract them. How far did you actually run if you started at 10 and ended at 100? Yeah. Most kids intuitively get this because you're like, well, just subtract them. From 10 to 100 is 90. Well, that's what this little symbol right here means. A triangle means change in. It's the physics symbol for, like, basically change in. So if I ask you for a triangle D with an arrow over top of it, here's what I'm really asking you for. Find me the change in displacement and give me a direction. That makes sense? Triangle means give me the change in displacement and give me a direction. And how are you going to find that? Well, you finished at 100, you started at 10, so like the answer to this question, I guess, would have been that you traveled for 90 meters, and we care about a direction, so you went 90 meters east. It looks intimidating at first, though, doesn't it? Like, if I show you this formula without context, you're like, whoa, what's that mean? What's that squiggle mean, right? And that's where when you see, like, in popular media, like, you see, like, some crazy Big Bang Theory, for example. They have their crazy diagrams on the board. Well, the biggest struggle is, well, what the heck does each symbol mean, right? Because like each symbol has its own meaning. So slowly but surely, we're going to build up your repertoire. Make sense? Can I change? Okay. So I want to give another example here. Let's say that you wanted to drive from Edmonton to Peace River. I don't know why you'd want to, but let's say you had to. Okay. One of these right here, the red line. See how the red line just kind of goes a little bit here, there, and everywhere? Because you go a little east and a little west. And when we make our roads so that they like are easy to drive on the terrain. You know, like they go between mountains and through valleys. You know, but like if you could fly from Edmonton to Peace River, you'd go in a straight line. You get what I'm saying here? So here's your question. Which one's the distance? Which one's the direction? Sorry, which one is the distance? Which one's the displacement? What was that? Displacement is red, is what you say. Why? What makes something a displacement? What's the one difference between displacement and distance? One of them has a... Okay. Which direction are you traveling in the red line? We're kind of traveling all directions, aren't we? So the red line really cannot be a displacement because displacement needs to have a direction. But clearly it goes north. Then right here it goes like west. And then it goes kind of over east again and goes north. Maybe even one little place in here is turn around go south for a bit. Do you guys agree though that like the red line is not going a consistent direction? So because this one has no direction, at least no consistent direction, this one right here, the red line, is the distance. I can tell you how far you've traveled, and you guys know how on road signs, like it says right outside of Fort Macleod, 50 kilometers to Lethbridge. Does it say 50 kilometers west or east? Well, no, because are we always traveling east? No, we go all over the place, right? Okay. Whereas if I could go in a consistent direction, I'm going to get this door over here. Okay. If you're always going in a consistent direction, I could then tell you that this one right here. Are you guys finished, by the way? Sweet. Every time you hand something in, this little black like kind of tub right here is where you throw it. Just make sure your name's on it. No, far one over there will do. Thanks, guys. By the way, that goes for you guys too. Whenever you need to hand something in, put it in this little tub over here. I got distracted there. Did I describe this well enough, though, you felt? Because this one right here, the displacement is going to be the black line because it has a constant direction. What would that constant direction, I can't spell. That's direction. What is the constant direction? Like north, west? Does that make sense? So I could tell you that you traveled this far, but I could tell you that it was northwest. Moving on. Okay, so try a little silly little scenario here. You are going to start right here. Start. You're going to walk 3 meters east. 1, 2, 3 meters east. You're then going to turn around and walk 5 meters west. Here's my question. What's your distance and what's your displacement? So let's talk it through. Which one do we care about direction in? Do you guys remember? Look back in your notes. Which one do we care about direction in? Is it distance or displacement that cares about direction? Displacement. Okay. So let me write that one with the D with the little hat on top. D with the little hat. Okay. If we care about our direction, let me start at the beginning here. I went 3 meters this way. I went 5 meters this way. From start, how far am I from my start? 2. But 2 meters, which way? West, right? Because didn't west win because you went more west than east? So if I ask you about your displacement, I mean, in a way, you just kind of look at it and you say, well, I started here, I went back this way. From start to finish, 5 minus 3, that must be 2 meters. So the answer is 2 meters, but you have to tell you that you ended up going west. That make sense? I mean, in theory, depending on how the numbers worked out, you could have ended up being east, right? Like if I took 10 steps that way and 1 step back, then it would have been east that wins. So let's try the other one then. What's the distance going to be? You got it. 8 meters. Do we need a direction on it? Well, no, because he didn't go the same way the whole time, right? Whoever is walking here walked a total of 8 meters, but has a net displacement of 2 meters west. And that little tweak there kind of makes a difference on things. Does that make sense? So that's the first thing we've learned. Distance and displacement. I had the exact same scenario in both cases, but like I have a different answer depending on context. If you care about direction, it's different if you don't care about direction, right? If I could fly from here to somewhere else or drive, I mean, okay, flying is faster because you go faster, obviously, right? But the other advantage to flying is you go in a straight line, right? How much better would it be if I could drive from like here to Lethbridge and it was literally, well, okay, it is pretty straight actually. But imagine that it was I was going in the mountains. Anyone ever go to BC? I live in BC, right? And if I didn't have to like wind all the way through, if I could just literally go in a straight line, they like dynamited the whole thing through, made like a one straight line tunnel. Wouldn't that be so much faster? Right? Okay, I think I made my point. Okay, well, you know what? Just like with distance and displacement, direction mattering, speed and velocity work the exact same way. Okay, speed refers to how fast you're going. Velocity then refers to how fast you are going. Keep going. Exactly, you got it. Does that make sense? So the way we use that is V is the letter we use for velocity. And if we care about direction, we put a hat on top of it. We also use V for speed, but since speed does not care about a direction, we don't put a little hat thingy on it. That's all. So for a similar analogy or example, I drive 110 kilometers an hour always. I do. Always. Who's laughing? Okay, that would be a speed. I drive 110 kilometers an hour, right? But if I drive 110 kilometers an hour west, now it makes it a vector. You know what I'm saying there? Okay, cool. Okay, that's what's on this slide right here. I do this a lot, by the way. I'm not the kind of teacher who's going to stand here and read off your slides. I hate that, by the way. It's my biggest pet peeve. I hate people who they try to teach by doing this. Speed is the distance traveled by an object during a given time interval divided by the time interval. Any questions? You like the hand on the hip there too? I will not read directly off my slides, by the way. So, but that's more or less what I talked about here, is that speed is a distance divided by time. Velocity is displacement divided by time. Okay, one of them involves direction values and one of them doesn't. Okay? So it actually leads to our first formula, which is on this slide right here. This is our first formula. If you ever want to know a velocity or a speed, you need to take your distance and divide by time. Now, here's the way the rules work. If you want the arrow hat on top, then this guy better have an arrow hat. If you don't want an arrow hat on top, then the other one doesn't have one. So like either you care about direction or you don't. That's basically how it works. So this is your formula, and I started to show you guys this last day. Okay, so another word I need you guys to know is called uniform motion. Uniform motion basically describes that you're always going the same speed. Okay, you know how like in your car you can speed up or slow down. If you put it on cruise control, that would be considered uniform motion because like everything is like the word uniform means the same in some contexts. Right? So like if you wear school uniforms, you're all wearing the same thing. Right? So uniform means going the same speed, and what I'm saying here is that you're always going that same speed. You're not speeding up, you're not slowing down, you're always going straight line. So here's my question then: a car traveling in a straight highway with cruise control set to 100 kilometers an hour, is that uniform motion? Yes. Yeah, he's always going the same speed. I'm sitting right now. Uniform motion? What's my speed? I'm not moving. 0. I'm actually under uniform motion right now, by the way. I'm not moving. Does that make sense? It's kind of sneaky. But like, if what you're doing is consistent, right now my speed is 0. It's still 0, by the way. Yep, nope, my speed's still 0. All right. Since my speed's not changing, it's consistent. It's uniform motion. Okay, let's try an example here. This is what I was trying to show you guys last day, with the idea of being able to do the math. This is what I think so many students, they freak out with physics because they're like, they got to have good math skills. And you do, but hopefully I can illustrate this well. The formula you need, I'll even use colors again, is that V equals D over T, only I want to think, oh, you guys see how I put the little triangles on this formula right here? You guys know what the triangles mean though now, right? Triangles mean No, triangles mean change in. D means displacement. Triangles mean change in. So what this really means is the change in your displacement over your change in time. Basically, how long were you working for and how far did you get? So, okay, so let's try this one here. Now that I've got this example sitting here, I've got 3 variables, like 3 letters. Okay, I'm going to plug 2 of them in. So I'm going to erase D, because don't I have D? Which of those 2 numbers up there is D? Yeah, 10, right? It says in the question that whoever it is, Buddy walks 10 meters. That must be a distance. And then it says that he walked for 5 seconds. 5 seconds is a measure of time, so then I should divide by 5. All right. You guys don't need a calculator for that, right? 10 divided by 5? 2. Okay. If you need a calculator, by the way, you can have one. Like, not everything is mental math. So we've now learned the average speed of the person is 2. But here's the really important thing, though. We need to have units still. Because, like, 2 on its own, that's math. Okay? Science needs to have two whats? 2 coffee cups, 2 years, 2 meters. You know what I mean? Like, you actually have to quantify it, which is why I started our lesson with that. You have to know what you're talking about. So the units are going to be, well, you walked 2 meters per second. That's actually a really common way of measuring speeds, meters per second. We also use kilometers per hour sometimes. That's another way of measuring them. But meters per second is a good example. So there's our speed. And if I were to ask you notation-wise, I would just use V. I would not use V with a hat over top. Why not? Yeah, I don't know which way she went. Based on the picture, I guess I could say that she went towards the right, I guess. No, but I mean, is that north, south, up, down, left, right? I don't know. That makes sense? Cool, moving on. Let's try a little bit more of a challenging question. Then we got to work backwards. A toy car travels at a speed of 15 meters per second. Okay, right off the bat, speed is 15 meters per second. It means that in that formula, V equals D over T, I know that the velocity is 15. Okay, it says it travels for 16.8 seconds. Okay, so 16.8 seconds, that's time, right? So wherever we used to have T, replace T with 16.8. And then what we don't know is the displacement. So I'm going to solve for D. So here's where the math comes in. I did this yesterday with colors. Was that helpful when I did different colors yesterday? Here, let's try this. 15 goes here. I'll make this D up here. And then I'll make yellow can be 16.8. Ooh, that's hard to see. It works for them though. How do you get D by itself, math-wise? Cross, multiply, and divide. Take it. Go ahead. Do we need to divide anything? No, because D, it's like there's a 1 in front of D. Now, some kids, they get a little ambitious and they say, oh, I'll divide the 15 down here. Here's the problem, though. Now is D back being by itself? Well, no, because now 15 is back on the bottom. You may as well cross multiply back up again. So grab a calculator or a cell phone or whatever. 16.8 needs to multiply by 15. That's kind of what's implied. Because it's cross multiply and divide. So grab a calculator. What's 16.8 times 15? Say it again. 252. Thank you. Wait, now we always need to make sure we finish this properly, though. 252 is math. We're in science. So I need to have a couple more things. I need to have at least a unit. Like, what are we talking about? Well, if you traveled 15 meters per second, and this was in seconds, like, I don't know if this makes sense here, but you did meters per second, and you times by seconds. In a way, like the seconds kind of cancels. What's the unit that you're left with? Well, meters. Yeah. So, okay, meters. But hang on a sec. I asked for a displacement. Does that include a direction? Okay. Well, the good news, I said we were going east. So, by the way, if you didn't clue into this, because I don't think I've said it yet, but standard convention, square bracket, and like a letter is usually sufficient. So square bracket E means east to most people. Square bracket L means left, probably. Yeah, 16.8, and I multiplied by 15. Does that work? Okay, one more thing. This still isn't notated properly, actually. Can someone pick out where my last mistake is? It's a little thing. It's not like the end of the world, but like it's a little thing. Having that little arrow hat on there. So that makes sense? Awesome. Okay, I've got some more examples sitting here, so I'm going to talk over Charlene because we're running out of time, but I really want to finish this because we're on a good day. You guys feel like this is a good day? Sweet. I'm pleased. Okay. I haven't taught most of you guys before, so this is my first day with you. I got some more practice questions here, but if it's okay, here's what I'd like to suggest. Try these on your own then. Okay, I've given you a little bit of context to start with. Give them a try, and then later ask me to look them over. Okay? One of the things I want to encourage you guys is don't be afraid to fail. I even put a poster literally up there on the wall that says failure on it. It's important to make mistakes once in a while. So like, try it, and if you don't get it wrong, I'm not a yell at you kind of teacher who's like, oh, how do you not get it right? Like, I will help you fix it. So like, try these and see whether you can do them yourself. No? So. Okay, I want to do our one last formula. The last formula we need to talk about is called acceleration. If you have uniform motion, you're always going the same speed. But how boring would it be if you only ever went the same speed? Yeah. Fortunately, we can speed up and pass that really slow semi. Or, this is actually even more important, we can slow down so that we don't crash into things, because that would also suck. Right? So we do need to be able to accelerate. Actually, we use two words. Acceleration usually means you're speeding up. And if I use the word decelerate, that would mean slow down. That makes sense? So there's actually technically two ways to accelerate an object. You can actually change its speed and make it go faster or slower. This doesn't really apply to you guys, but in higher levels of physics, you can actually accelerate an object by changing its direction. If I spin stuff around in a circle, it's actually accelerating it, by the way. You know, like if you ever have like a, I don't know, something on a string and you swing it around, you're actually accelerating it, believe it or not. Even though it might be going the same speed, because it's going in a new direction, it speeds up. You guys ever go around the curve going out of Lethbridge and take a little bit faster than you should, and you feel yourself kind of like thrown into the door of your car a little bit there? You're actually feeling what's called centripetal acceleration. You know, so don't do that when it's icy out, because then you'll spin off the road or something like that. I did that once when I was younger. Anybody ever been to Sparwood? There's a big curve in the road there, and I took it too fast on ice, and like I wasn't able to like keep my you know. I don't actually say this was a joking thing. It was terrifying because like it was really icy out, and so like I'm trying to make the curve, but like I can't make the curve. My car couldn't withhandle the centripetal acceleration of making a curve, and so like I ended up like going into oncoming traffic and doing a few donuts in the middle of the road, but like no one was driving the other way, thank goodness. But it was like one of those moments. So, anyways, I got a topic. Here's the last formula we're going to learn today. It's A equals V over T. Okay. Anyone want to hazard a guess what A stands for? There we go. Yeah, I mean, we picked these letters on purpose, right? So if you ever want to find an acceleration, you need to know your change in velocity and your change in time. Now, it could be with a little arrow hat on top. It doesn't have to be. No. For some reason, I wasn't consistent. Here, I put the arrow hat on top. Here, I didn't. Okay. But like, it's very, very similar to what we just did. So let's try an example. Oh, actually, I have an example here first. See how there's these different cars in this little animation I've got right here? Which one of these cars has the best acceleration? Did that make sense to everybody? Well, okay. How about we talk initial acceleration? Yeah, red got off to like a boom of a start, right? But here's the problem with red. Red has a very low top speed. You know how like you say like a car goes 0 to 60? That's red. Only red went like 0 to 20. And then red craps out and is stuck at 20 the whole time, and that's all it could do, right? In terms of best acceleration, though, it is red. Red has the best initial acceleration. However, blue eventually gets to a higher top speed. You get the difference there? So acceleration is like how fast you like step on the gas, but that's different than how fast you can go. If I got a car that can go 230 miles per hour, that's a very high top speed. But what if it takes like 10 minutes to slowly but surely get to that speed? Well, it has no acceleration. Anyways, here's our example. Let's say you have a boat. The boat can accelerate at 4.5. By the way, I didn't mention this because I'm shortening things up a bit. Meters per second squared. This little 2 right here means squared. Is the unit for acceleration. I'm going to give you a change in speed of 18 meters per second. Holy I know, we gotta hurry here. My question now is how long is it gonna take? So, first thing we need to do is we need to figure out which formula we need, and it was just on the last slide, right? So I'm gonna use colors to help us with it again. We'll do A being in purple. This is our last example. We're cutting it close. I'm a mean teacher. Okay. We want to put our change in velocity up top here. And we want to put our change in time down here. Everybody cool with that first part? Okay, let's start erasing things. I just wrote them, now I'm erasing them. Let's erase what we know. We know the acceleration was 4.5, right? So I'm going to change this one out right here. And I'm going to make the acceleration 4.5. What's the other one I can erase and replace? Yeah, speed. But change in speed, right? It says we changed our speed in 18.5. I don't actually know what our speed is. Our speed could have been 0, and we went from 0 to 18.5. We could have been at 1 and went to 19.5, or 2 and 20.5. So I don't actually know what my speed is, but I know what it changed by. So let's erase this guy right here. We're going to make it. Let's make this one 18.5. Now is the math portion. How do I solve this? Yeah, cross multiply and divide is the concept. You're right. I think you got the idea. Let me visualize this for you. You want to take this change in time right here. We want to cross multiply it to there. Does that make sense? That's the cross multiply part. Now, in the previous example, we didn't have to divide because there wasn't a number next to the t, but you guys can see the 4.5 sitting right here, right? So we divide the 4.5 down that way. So grab a calculator. 18.5 divided by 4.5. Anybody got one? What'd you get? Cool, let's call it 4.1 then. Okay, last thoughts. That was math. But good science requires quantitative values, right? So what's the units for this? Yeah, seconds, right? Doesn't that make sense? I mean, wasn't this in meters per second and this was in seconds? Isn't the unit going to be seconds? Okay. One more thought. Direction. Is time a vector or scalar? Is time a vector or scalar? Scalar, yeah. You never, if you guys noticed here, there was not a little arrowhead over top of this, hey? Time is not a direction, so we don't need a direction. So there we go, we're done. This is how long it'll take. That was my last slide, right? Cool. Okay, that's it for our day. Any questions? How was that for kind of our first lesson together as a group? Successful? Okay, passing advice as you're packing up, because I think you're looking for me, aren't you? Give me one more second, okay? Passing advice here. When you guys come back next week, then make sure you have topic 2 notes printed off, right? Make sure you have your assignment printed off. We're going to start working on that. Okay, one more heads up. I'm actually not here on Monday or Tuesday. I'm going to the Super Bowl. So, yeah. So I'm not going to be here Monday, Tuesday. So what I'm going to have you guys do on Monday is you guys are going to watch a YouTube video of me teaching, okay? And then on Tuesday, you're going to do some work time. And then when I come back, we're going to get back into this together, okay? Sound good? Woo! Okay, thanks, guys. See you later.